Hello, welcome to this topic on functionals. In this class, I'll be talking about functionals which are used in the context of density functional theory. So you all might be already aware of functions, which you might have come across in your high school. So basically, a function is a map or a rule that basically takes a number and gives out another number y. Okay, so what it basically does is you have two sets, a and b. So here we are talking about functions. So you have two sets a and b with elements as given. Okay, so what a function, let's call it f, will do, it will map the elements in set a to elements in set b. Now the mapping can be one-to-one, or it can be many-to-one. Now one-to-one means like each element here is mapped to one element here, and no two elements in A are mapped to same element in B. So that's what we call one-to-one mapping. Many-to-one mapping is that every element in A maps to some element in B, and it's also possible that two elements in A may map to the same element in B. For instance, if I give example for one function, it would be a linear function ax plus b, where a and b are constants. So this would be a one-to-one function. And then we can also have, so let's call it 1, 1, and then we can have many-to-one, which is something like x squared. Okay, so you can give plus minus 2 and both will map to 4. So this is the basics of function, which I hope you know. But in today's class, we'll be talking about what are called functionals. So functional is basically uh, written as like this. And what it does is that it assigns a number to a particular function here, f of x, and the functional is denoted by the capitalized letter, right? So if you give it, so say suppose it's some kind of a functional, and if you give it a function, it will give you out a number, say k. Okay, now this is the focus. This will be the focus of today's class. Uh, Before that, I would like to say that the functionals are mainly used like functionals are mainly used in theories like density functional theory. So this class will be relevant for people who do DFT. Now, let me give you a more better example. Say, suppose we have a polar function given by r of theta, which is periodic in the range 0 to 2 pi, right? So what it will define, so say suppose we are defining a simple surface like circle, something like this, or maybe ellipse, right? So there will be similarly many kinds of such uh, such curves in 2D, which we can define. So for instance, so one more we can define is theta equal to 1 plus cos theta. So if you have taken a course in trigonometry or polar coordinates, you might have seen this kind of figure often. What looks like a beam. So one more figure will be something which I can write. One more sine 3 theta. Okay, so this one looks like something like this. So all of these are just surfaces, or you can say figures in 2D. So, and the boundary of these figures basically, of the shapes basically bound have an area. So they enclose an area. Okay, so they will have some area, or if you are interested in measuring the circumference, what you call the perimeter also. So these are some of the properties of these shapes in 2D, fine. Now what I am interested in doing is I want a functional, let's call it A, such that if I give it any of these shapes, it should give me a number, which that number is basically area. Okay. Similarly, I want to define a functional, let's say P, such that whenever I give it any function, any of these closed curves, it should give me its parameter. So that's what I'm interested in, finding these functionals. So a functional basically takes in a function and it will assign to it a particular number for which the functional is designed. So similarly, in case of in DFT, density functional theory, we have energy functionals. So you give the electron density and it gives out you the energy for that particular function. So let's try to do some examples so that we can understand it better. So here, let's try to first find the area function. Let's see how it looks like, area function. So consider some figure like this, okay? And let's say, suppose we have here some point, and we are interested in calculating the area bounded by this curve, fine? So what we will do is let's call this point as O, this point as A, and I rotate it by some angle, small angle, let's say d theta, such that it comes here B. Okay, and this distance OA is R, and since I'm assuming the angle d theta is very, very small, so I will just say that OB will be also approximately R, fine. And then let's say that this subtends here right angle, fine, for very small theta. So then if you see, if you calculate cos of theta, what you will get? You will get R, basically you will get, okay, let me write it. Okay. So what you will get is OA by OB, which will be approximately like R by R. So you can say R cos theta is equal to R. Right? Similarly, you can find the sine theta, which will be AB by OB, such that your AB will be R. Okay, okay, I made a mistake. It should be d theta here, such that this will be R sine d theta, fine. And for very small d theta, then I can approximate it as d theta, fine. So this will be AB. Now for this small triangle here, if I wish to calculate the area, then the area can be given as, for this small triangle, half AB OA. And if you see, then we will have AB. What's our AB? AB will be R d theta, and our OA is going to be R. So what we will get is R square d theta by 2. Now this is the area of this small triangle here. I shade it. So this is the area of this small triangle. But what I am interested in is to calculate the area of all of this shape that's bounded by this boundary. So for that, what I will have to do is integrate it over 0 to 2 pi. So if I integrate this area from 0 to 2 pi, then I will get the complete area. So that's what we are going to do. So the area then will be a function of function, which is R of theta, that means this r of theta defines this shape, then the total area will be 0 to 2 pi r square theta by 2. So then this is what we call the area function. So what this function will do, you have r theta for some curve, you give it as an input to this functional, and it will give you the area of that curve. Fine. So this is how functionals basically work. You give them a function and they give you out some number which is related to that functional. Fine. So similarly, we can define. Okay, before that, let's do some example. So let's try to use this formula to see whether it works or not. Say suppose we have a circle. Let's write on circle. So for circle, you have the rectangular equation as this. If you want to convert here, the radius is 1. If you want to convert it into the polar form, so you will have to substitute for cos theta for x. Times theta equal to 1, and then you will have r square equal to times square theta, which is again equal to 1. So what you'll be doing, you will just put here 1, and the area of circle then will be 0 to 2 pi d theta by 2, which is pi. And if you know from the basic formula for circle, calculate the area is pi r square, and in this case, since r is equal to 1, and we exactly get the same answer. Right now, let's try it on some another curve. Say suppose ellipse. So for ellipse, let's say suppose we have a formula like this. So let's first convert it into the polar form. So we will have right, and then we can write it as theta, right? So what we'll do is we will just plug this formula into the area functional, which will give us right. And to simplify, to solve this integral, we'll just convert it by dividing numerator and denominator by cos theta, cos square theta, which will basically give us x square theta divided by 1 plus 4 tan square theta. Fine. So a little bit of more algebra. We can write it also as fine. We can write it as this also. And then what we will do is, and we have here secant square theta. Now, what we can do is we can substitute for tan theta, and we will have d theta sec square theta as, so if I use tan theta equal to z, I will get secant square theta d theta equal to dz. Okay, and then if you check for the limits, so it's 0 to 2, but there are discontinuous at pi by 2 and 3 pi by 2, so you will have to basically split it. So you will get, so you can split it into 4 parts: 0 to 2, 0 to pi by 2, pi by 2 to 3 pi by 2, 3 pi by 2 to 2 pi. So there will be just 4 parts because of the discontinuities. So which all of them will be the having the will be the same. So you can just integrate it from only 0 to pi by 2 and multiply by 4. So what you will get is then 0 to pi by 2, 4 divided by 2. Then you have this 4 here. Then you have dz 1 by 4 plus z square. So that's your final integral, and the 4 and 4 will just cancel out. So you will have 1 by 2 right. And if you remember this integral from your high school, this will be just equal to tan into 1 by a, right? And this 1 by 2 and this 1 by 2 will go away, and you are putting the limit 0 to pi, 0 to infinity. So tan obviously is tan inverse. So tan inverse infinity will be pi by 2 and 0 will be 0. So the final value will be pi by 2. Now let's try to confirm. Now you know for an ellipse with A and B, the area is basically the area of ellipse is given by pi AB. Right, now let's see if we can get the same answer. So the equation that I used was, let's just try to find A and B. So you will have, so in this case, A is 1 and B is half. So then area will be from this formula into 1 by 2, which is pi by 2. So yeah, we got the same result. So then this functional basically here that we derived will give you area of any bounded curve if you know it's r of theta. Okay, so that's how we basically define these functionals. And this is the difference between the functional and a function, which in case of function, it is just a number mapped to a number. Here in case of functional, what it does is basically it assigns a number to a particular function, given like in this case, r of theta, which will give you the area. Let's try to do it on some more examples, or let's try to derive some more functionals. So derive parameter functional. So we'll again use some surface, suppose like this. Okay. And let's call this thing here. So let's define this as O, A, and let's call this thing as B, and let this be R. Okay. Let's try perpendicular from here, such that this is here 90. Fine. And basically, let's just assume that, I mean, if I just zoom this part, then let's assume that this here forms a triangle. Okay, and assume it, let's suppose this is something of O, this is here d theta. Let's call this A, let's call this B. Okay, and let's this be C. Fine. So what we are interested in is knowing AB, which is the small part of this whole parameter. Fine. And once we find AB, then we can just integrate over 0 to 2 pi to get the complete parameter. So how do we get AB? So for AB, we need to first know AC. Now this thing here is R, A to 0, let's call it R. Then same wise, C to 0 will be R. The small increment here, let's call it dr. Fine. So let's try to find sine d theta. which will be AC by R, right? So that we can say AC equals to R d theta for very small d theta, fine. And now what you need is you need to find AB. So you can now apply the Pythagoras theorem. So you know AC, you know BC, which is dr, and then you can use theorem. So let's see what we will get. So then this small parameter we can get as r square d theta square plus this thing, right? But since we are interested in calculating all of the parameters, so we will have to integrate it then over 0 to 2 pi, which will give us r square d theta square plus dr square. And if we can write it this way, you can also write it in this way, right? So then this gives you basically the parameter function. Then this will define the parameter functional, which basically what it will do is that you have some kind of curve, and you know it's r of theta, which basically describes it. You plug this thing into this functional, it will give you the parameter. So this will be then the parameter functional. So that's how we define these functionals for these functions. As an example, let's try to on a simple case, say suppose circle. Let's see if we get the right answer. So for a circle, again, r of theta we know is 1, right? So then what we will get, r of theta will be 0, 2 pi d theta root 1 plus, now the derivative will be 0 r dash because it's constant. So it will be just 0, and what you will get is just 2 pi. Now you know parameter of circle in general is 2 pi r, and in this case for r equal to 1, you will get 2 pi. So yeah, you are getting the right answer, right? So then this is how we define these functionals. So by now I hope you have understood the concept of a functional and how we define them and how they can be used to get some property of a function. Now let's move further ahead. Uh, let's see if I can introduce some examples. Now let's basically try to look more into these functionals. So if you see these two functionals, so if you have this area functional, which is given as 0, 2 pi r square by 2 d theta, right? And you have then this perimeter functional, so what's the difference between these two? So this first one, the area only depends on the value of the r at a particular theta, right? But in case of perimeter, it depends on its derivative as well. So the area functional is what we call local function. And in this case, parameter, we call it semi-local function. This is what we call the semi-local function, right? So any functional which depends on some function r and its derivatives, whether first, second, third, etc. So that's what we call the semi-local functional. And a functional which just depends on the function is what we call the local function. Now we will look next into the how we can find the derivative of a function. Now why we need to look into that? So if you are doing DFT, you might be well aware that we need to minimize energies. We often, I mean, people who do quantum mechanics, you know that we often need to minimize the energy of a system. For that, we need to take a derivative. And in case of DFT, what we have is we have this energy functional, which basically depends on the electron density, right? And when you have this energy functional, one is often interested in minimizing so that you can reach the ground state energy for a given density, for a given electron density. And for that, you will have to know how we can differentiate a functional, right? So the next, we will then discuss about the functions, the derivative of a functional. Initially, we will start from a basic functional. Say, suppose, let's take the simplest case, which is area functional. Let's see how we can differentiate it. Fine. So from the concepts in functions, if we have to differentiate a function, what we would do, we would just increment the variable by a small change and then subtract it by the original, divided by the change under the limit that it goes to zero, it tends to zero. And that's what we define as the differential. Fine. So we will use the same concept here. Fine. So what we need to do is we need to add a small change to the function and see how it changes. Then what we will have is our if we try to use binomial theorem here, what we will get is now, since this change is already very small, then delta r square can be ignored, considering only the first order terms. Then we will have fine. Let me simplify it a bit more. So you can write it as r square by 2 d theta plus it is a 2 as well. Now, if you recognize this thing, this term here, this is nothing but just the original term, right? So you can take it to the left, which will give you and the 2 will go. So you will have finally in the end something like this. Now, if you since it's a change, if you take it very small, let's say suppose you substitute as this, so since this is the change in r, so let's take it very small where e tends to 0. Then you can write it as this. Then to calculate change, you will get this will then become r epsilon. Okay, so if you want to solve this integral, so r of theta will just become r of theta naught, and epsilon can be taken outside, and the rest of the integral will be 1 as the area under the delta function is 1. So what we will there have is okay. Ready. So what you'll have then is r of theta naught. Fine. And then in that case, we can then define the derivative of a functional, for example, the area function as this, right? Which is basically written as, so then the derivative of functional a of r will be, in this case, r theta. That's how we define the derivative of a function. Now here I used it epsilon delta naught for this change in r, but in general, if you have to write it in general, now if you compare, what you get in the end is just r of theta. So if you see into just into this equation here, this equation, then this thing here is what you define is, then this r of theta here is what you can call the functional derivative without having used this thing here. So you'll get, this is called the functional derivative. Fine. So let's try to do it on a more general way than just doing it with some area function. So you'll get some better idea. Let's suppose we have some functional f of g of x, which we have as t of x and h of g of x. Now, why I am writing it as h of g of x? Because the term here can be g square x, it can be square root of g, it can be anything. So I'm just writing it as h of g of x. Fine. Now, the rule is to find the little change in this function, which will give you. Fine. Now, what you do, you'll just use Taylor series to basically expand it, which will give you h of g plus delta g dou h by dou g, and then there will be higher order terms. Fine, which we will be ignoring. Then what you will have h of g plus delta g. Think fine, and if you again recognize the first term here, the remaining terms you can write which will be 2 pi delta g dou h by dou g dx. And when you have calculated this thing, then the way we define the functional of this, the derivative of this functional is in this way, which is to be written as dou h g of x by dou g. So this is the same way as we did here, where we just used this substitution for the change in that delta r, and we got r of theta. But in general, this is the way how we define the functional derivative. So what you do is you basically calculate the change in the function, subtract it with the original function, and then you express it in terms of as is shown here. So what you require is an integral d of x, the change in the function, and then whatever is remaining will be the functional derivative. Fine. Now let's do it on some more examples so that you can understand it better. So let me try it out on the parameter function. Let's try to differentiate the parameter functional to see what we will get. So how do we define the parameter functional? Defined as 0 pi theta r square r dash. Now let's try to find the functional derivative of this thing. So the steps are as, first we find a change in the function. Next, let's try to expand the terms. We would have r square fine. Now these terms here will be ignored because they're second order terms. So we can just neglect them because delta r is already small. What we will have then is theta square r dash square. Fine. This is what we will have. Now let's since r square plus r dash square is already larger than these terms, so we will just take it out so that it can go into the denominator of the for other terms. What we will have then is there is this big square root. Fine. Now you can apply the binomial theorem because now the term here is very small, this term. So this term here is now very small than one, so you can use the binomial theorem. And when you apply the binomial theorem, what you will get is one plus we will just keep only the first two terms, the constant linear term. This is what we would get. Fine. Now again, if you recognize here we have one and then this term, if you just multiply these terms to the one, what you would get is nothing but P of R. So you recognize P of R from here. So you can take it on the left side, and then what's remaining on the right side will be so this is then what you would get, right? So this is what's then remaining on the right hand side. Now, what we need to do is we need to express it as this, as I've shown. So you need a change in the function, that's delta g dx, and then whatever is remaining becomes the derivative of the function. So you will need delta r. So you have delta r here, but you have a derivative of delta r here, right? So we will need to convert it to delta r. So how we do that? We will use integration by parts on the second part. Okay, not on the first part because we need to change this to delta r, right? So we'll be using, so let's call that thing at j. So let me write it here. So what we need to do is we need to find integration by parts here. So I'll be taking r dash this thing out, and what I will have inside is this thing, and then I would have d by d theta r dash thing, and then you would have delta r d theta. Yeah. Now this term here, first term will go to 0 because since the function is periodic, so integrating it over, these will give you the 0. And what you will have then is the theta, this thing, the theta, fine. So let's plug it back into this equation here in the top. So what you will have, then you would have minus d by d theta r dash delta r. Fine. So this is what you would get. Now you want to bring it in the form that I was talking about. Then you have delta theta, delta r you can pull out, and whatever is then remaining becomes your functional derivative for this parameter function. So this thing will then become your uh, derivative of parameter functional, which you can write as yeah, that's it. So that's how you can basically calculate the derivative of any functional by using the same method. Fine. Um, now here what we did was we tried to calculate the derivative of a semi-local functional. Fine. So we used this ab initio, I mean like the first principles approach where we did it by calculating the change, then subtracting the original functional, and then getting the result. But now let's do one thing is that let's now try to derive a more general formula for the functional derivative of a semi-local functional. Okay. Now, before that also, so here what you will have to do is since r is a function of theta, so you can basically differentiate it a bit more, and then you can do some kind of algebra to arrive at a final formula. So I will just leave that as an exercise. Okay, but this here is also the in a good form that we can call the functional derivative. So let's now derive a general result. Derivative of a semi-local function. So consider a functional of the type which basically depends on n as well as its derivative. Fine. And now what we are interested in is to find the general formula for the derivative of this function. So how we will do it? By using the same approach, we will first add a small change. Fine. And then we will use the Taylor series to expand it, which will give us and we will ignore all the higher order terms. We will only keep up to the linear term. This is what we will get. Fine. Now, again, if you recognize this term here, this is nothing but b of n. So you will just take it on the left side, and what you will get then what you will have is d of x the n dash here is the derivative of this function n of x, fine. Now we need to bring it in the form that we were talking about. So we need dx, which we already have. We need delta n. So we have here, but we don't have here, so we cannot pull it out. So we will have to basically reduce the order of this delta n dash here. And how we can do that is by integrating by parts. So I will just take let's assume, let's call this thing as j. Let me do it separately. Then I'll have this thing here, fine. And after integrating by parts, what we will get is this thing. And yeah, one more thing. Let's assume the limits are from minus infinity to plus infinity. And also we'll be making one assumption here. Let me write it down. So the assumption we'll be using is that all derivatives of this functional, I mean this functional basically go to zero at the endpoints of the limits. Okay, so all derivatives basically go to zero at the endpoints. Okay, okay. So then what we will have is uh, all endpoints of the n of x basically go to zero and all its derivatives at the endpoints. So then we will have this thing here, and then we can write the same thing as d by dx. Delta n dx. Now this thing will go zero because of the assumption. It's a bound, and because and also because it's a bounded function, that's why we need to take this assumption. And then we will have this thing, fine. Now what we'll do is we will just plug it back into here, and we will have and what we finally have is yeah, now we can bring it in the form that we want. We have dx, we have delta n, and whatever is remaining inside is the functional derivative. Fine. So I will write it as this is what we define as the functional derivative of a semi-local function. Okay. So let's try an example for this. Let's try it. So we have a functional, we have a semi-local functional. Basically, it's the energy functional, which we call as 1 p second functional. So it's basically a kinetic energy functional, which is given as you will often see these kind of functionals in DFT courses. Right? So N here is the electron density, and the dash here represents the gradient. So if we want to find the functional derivative for this functional, so one way is to just use the first principles approach, but that will be now very, lengthy. So we will just use this formula. Let's see how we can use this formula to calculate the functional derivative for this kinetic energy function. So what we need is, first of all, B of n. Let's identify B of n dash. So our B of n and dash is nothing but this thing. Okay, then we need to calculate the derivative of this with respect to the n. So if you calculate it with respect to the n, it's going to be 8n square, right? And then we need to calculate the derivative of same thing, but with respect to the derivative of the electron density, that's n dash in this case. So 2p by 2n dash is going to be 2n dash by 8n, which will be just n dash by 4n, right? And then we need to calculate the derivative with respect to the x. So this thing will give us n double dash, if we can use the UV rule. This will be, I think, n square. You'll have 4 as well here. And you'll have n dash more, so it will be square, right? Now you'll have to add this term here and this term. So let's do it. So what we will have is minus n dash squared by 8n square, and then you have plus n double dash by 4n and dash square by 4n square. Fine. Oh, I think I missed something. Okay, there is a minus also in this formula here. So this minus and the second minus will become plus basically. So this will be just plus, right? And this thing here will be then minus. Fine. Now the first and the last term, if you add them up, basically it's a subtraction. So this will give you n dash square by 8n square minus n double dash 4n. So that's how you can quickly calculate the functional derivative of semi-local functions. Fine. So pretty neat. So you don't need to go through the first principles approach, right? Now in DFT, you will often see we need such kind of derivatives when you are basically trying to minimize the energy, total energy of your system. So there you often have these functionals like Hartree functional. You have a functional defined for exchange correlation. You have a functional for the Hartree energy, the electron ion interactions, and kinetic energy. So there you will see often these kind of derivatives and pop-up functionals that we need. So in that context, let me show one more example, which we call the Hartree energy. So if you see the functional for Hartree, so the Hartree functional is given as it's a local functional, fine. And here n of r is the electron density. So what we are interested in is basically calculating the functional, the derivative of this functional, and what this defines is basically the interaction between the electrons, the electrostatic interaction between one electron and other electrons. So what we will do is we will use the same approach here also. So the thing to see here is that here we have electron density with two different variables. So what we will do is just use the same approach. Which will give you n plus delta n and n dash plus delta n dash. Please note n dash in this case is not the derivative, but it just represents the variable r dash, r minus r dash. So this thing will give you n dash plus n delta n dash plus n dash delta n, and the last term we can ignore because it will be the second order term, and then you have r minus r dash. Now again the first term here, if you see, this is just u of n of r, so you can just take it on the left side, and what you will have then is so finally this is what you will get. Fine, this is your n dash. Now, if you look at this term here, which is inside the integral, the only difference is that here you have n of r, and here you have n dash, n r dash. Fine. From the perspective of this integral, r and r dash are just nothing but dummy variables. So essentially, both the terms are basically the same. So if you just interchange r with r dash, the integral does not change. Or even if you remove r dash and keep it as x, y, z, whatever, it does not change the value of the integral. So r and r dash are just dummy variables. And you can see the symmetricity in these two terms. So when integrating, they will both give the same value. So we can just keep it as a single term. We can write it then as twice we have, right? And we can write it as twice n dash delta n. Fine. So this 2 and 2 will then go away. And what we have finally is n r dash delta n of r minus r dash. Okay, and now we want to bring it in the form that we want. So we will have here delta r cube. We will have delta n here, and whatever is remaining then is your functional derivative. So yeah, the functional derivative of this R3 energy is then so that's it about derivatives and functionals. So we saw how we can calculate the derivative of a functional. We saw what functionals are. We also derived a general formula for calculating the derivative of a semi-local functional. And we saw that why it's necessary to learn why we need to calculate the derivatives. So essentially for people who are doing DFT, all this, I hope this will be very helpful. Now, before I finish, I would like to finally talk more about the derivatives of these functionals. So if you see, we have certain, so we basically approximate the exchange correlation functional in DFT. And one of the approximations used is what we call the local density approximation, which is basically a local function. And if I remember correctly, one of the local functionals is Thomas Fermi functional, which is a local functional. And then there is another functional, which is a much better than the LDA, which is called the GGA, generalized gradient approximation. So it depends on the electron density and as well as its first gradient. Then if you go up the ladder, we have what's called the meta generalized gradient approximation, MGGA, which depends on n dash and n double dash. So there is this thing called the Jacob's ladder in DFT, where as you go up, the accuracy basically increases. So generally, MGGA has a better accuracy than GGA and LDA. So if you are using MGGA, then you will have then you will have up to the second order of derivative in your functional. And if you want to know how to calculate the derivative of that thing, or maybe sometimes you will have a functional with which basically depends not only on n but up to some higher order derivatives. Okay, so now what we will do is basically we will derive a general result which will basically give you a functional derivative of any semi-local functional which is depend on derivatives up to nth. Right. So for that, let me define derivative of functional with nth gradient. Okay. So I will define it as f of g, which basically depends on say h of g, g dash, and g of n. Fine. And I will use the assumption that I used last time also, that g and its derivatives basically vanish at endpoints. Fine. So the first rule is to calculate a change in g, which will give you where gn represents the nth gradient. Okay, now we will use the Taylor expansion. And we will ignore all the second order and higher order terms. So here you will have then you will have the higher order terms as well, which we will ignore. Okay, let's call them ON terms. Then there will be delta G dash and the higher order terms. And then for the third one, you will have delta G double dash. And then again higher terms and so on. Okay, so I have taken only up to first three terms here, first three linear terms. Now, ignoring all the higher order terms, and finally what we have right, and then you have this delta G, H beta G, and then you have it and so on. Fine. Now again, this term here, first term is just f of g. So you take it on the left side. So now what you have is just delta G, dou G, and other terms. Fine. And then there is this dx. Now you want to get it in the form where you have dx, where you have dg, and the rest of the terms. So there's a trouble that here we have dg derivative and here we have a double derivative. So we need to reduce all of them to the dg. How we do that? We will do it one by one by using the integration by parts. Let's consider this as j. Let's call this as k. So for j, what we will have, as we did also earlier, integration by parts will give you delta g dx, and this thing will just go to 0. Fine. So this is the j. Similarly, the k is basically so first time integral by parts will give you this thing. Fine. And here then you will have delta g dash and dx. This term will go to 0. Then you will have minus here. Okay, then you have to now do again integration by parts on the second term so that you can reduce this thing to delta g. So you will have then minus d by dx with some limits. Let's call it lower limit, and the upper limit. Okay, so this will go again to 0, and then you have minus minus plus. There will be a double minus, which will give you delta g dx. Okay, now let's put all of them together into this term here, which will give us delta g dou h by dou g, and then you have minus d by dx dou h by dou g dash, and then you have this term here you have as well delta g, and then you have this dx for the whole term. Fine. Now you can, and then of course you have here other terms for higher order. I mean, not the higher order terms, for other like d cube will be there then and d4. So if you take out delta g, then what you will have is something like this. So you have dx, you can take out delta g, and whatever is remaining inside then is and so on. Now we only took here 3 terms, right? But if you see the pattern in these 3 terms is that you have first term where you have just dou h by dou g, then you have the first derivative, and here also you have the first derivative in g, second derivative here d2 by dx2, and here in g you have also the second derivative. So for the n terms, then the functional derivative will be then written as then the functional derivative you can write as okay, and in the compact form you can write it as I equal to 0 to n. There is this alternative sign. So for that you have to write this. And di represents the ith derivative. Similarly, gi will represent the ith derivative. So this is then the general formula for taking the derivative of a semi-local functional which depends up to the nth derivative. So in short, the rule to find the derivative, rule, or I should say, the method to find functional derivative is first step you find a change. So you will have some functional f of g of x. The first step is to find the change in g. Second step is to basically do Taylor expansion wherever possible. Third will be to calculate f of g delta g minus f of g. Fourth is to bring the form from step 3, or I should say maybe use some integration by parts if necessary. Let's say fourth step is integration by parts to reduce the terms, to reduce the higher order derivatives, okay, if necessary. And then the fifth is to bring it in the form integral dx delta g and some remaining function. Let's say let's call it fg. Let's say k of g of x. So then your functional derivative will be this remaining thing k of g of x. So this is the functional derivative. So that's it for this class. So I hope this will be very useful for people who are doing DFT. And if you have any questions, please feel free to contact me at the email ID given here. So that's it. Thank you.